In this lecture I want to clarify how crossover and mutation is done. In the previous video I mentioned crossover probability and you might wonder what that is. For each generation we select some of the fittest solutions for crossover. After we selected a pair of solutions, we decide with a certain probability if these solutions will cross over or not. We do that usually with a high probability towards crossover, about 70 to 100%. When we decide not to cross the solutions, instead of mixing the chromosomes from one parent and the other, we just pass the chromosomes as they were. You can think of it that instead of producing children, which are a mix of their parents, we just produce clones of the parents. How exactly do we select which solutions we want to cross over? Mainly there are two ways, but you can also think of others if you want to. The methods are called tournament selection and roulette wheel selection. For the tournament selection, we need a parameter which we will call k. K is usually equal to 3. We select a group of k random solutions, in this case 3, and evaluate the fitnesses of all the solutions. The one with the highest fitness wins, and that's the first parent. We pick another k random solutions and their winner is the second parent. Then we decide if the two winners will cross over or remain unchanged. For the roulette wheel method, it's good to arrange the solutions from the fittest to the least fit. Let's pretend we have a generation of 5 solutions. The best solution, the one in red, has a fitness of 36. The second one 28, the green one 20, then 10 and 6. The sum of all these fitnesses is 100. So we pick a random number from 0 to 100. If that number is between 0 and 36, then we pick solution 1. If the number is between 36 and 36 plus the fitness of the second solution, then we pick the second solution. The second solution has a fitness of 28, so the interval for this solution is from 36 to 36 plus 28, and that's 64. From 64 to 64 plus the fitness of the third solution, which is 20, we pick the third solution. So that's from 64 to 84. The same way from 84 to 94, we get the fourth solution. From 94 to 100, we get the last solution. So these are the two ways to pick the solutions for crossover. How exactly do we perform the crossover? The easiest method is the single point crossover. We choose a random point. Let's say we have 8 chromosomes and these are 8 bits. Also, let's say that the random position is at bit 5. One child will have the first 5 bits from parent 1 and the last 3 bits from parent 2. The second child is the other way around. First 5 bits from parent 2 and the last 3 bits from parent 1. A variation of this is the multi-point crossover. You can have 2 or more random points at which you cross over. Let's pretend we chose 2 random positions at bit 3 and 5. First child will have the first 3 bits from parent 1, bits 4 and 5 from parent 2, bits 6, 7 and 8 from parent 1 again. And of course the second child will be the other way around. First 3 bits from parent 2, bits 4 and 5 from parent 1, bits 6, 7 and 8 from parent 2. The final method is called the uniform crossover. This is where for each chromosome in part you decide if it's going to be from parent 1 or parent 2, and you decide that at random. After we perform crossover, it's time to do the mutation. For each solution we go through all of its chromosomes, and with a certain probability we decide if the current chromosome is going to be changed or not. How exactly do we change the chromosomes? For example, if the chromosome is a bit, we flip it from 1 to 0 and from 0 to 1. If the solution is a string, then we change the character with another random character. For the traveling salesperson problem, for example, we swap the order of 2 cities between themselves. And that's because you can't just change one city, as you will see in the coding example. A final word about the parameters. You have to play around with them and see which combination gives you the best results. If the mutation rate is too high, then that produces chaos and meaningless results. However, if the mutation rate is too low, then you might get stuck in a local minimum or maximum, like in the hill climb. You need some randomness to get out of it. Regarding the population size, if it's too high, then the program will execute slowly. If it's too low, then you will get worse quality results.